Hey everybody, here is the video to accompany homework number 5. I should share my screen. Cool. Move this. Right. More logs and simple interest. So we're going to start with some examples here. Given the following approximations, log of 2 is approximately 0.3, log of 3 is approximately 0.48, log of 7 is approximately 0.85, natural log of 2 is approximately 0.69, natural log of 3 is approximately 1.10, natural log of 5 is approximately 1.61, and natural log of 7 is approximately 1.95. We're going to approximate the following logarithms without the use of a calculator by using the properties of logs. A reminder on the properties of logs. We have the product property where the log of a product is equal to the sum of the logarithms. We have the quotient property where the log of x divided by y is equal to the log of x minus the log of y. I'm not saying base b, I could say base b. The log base b of x to a power is equal to that power times the log base b of x. And again, this is the product, quotient, and power rule. Although, again, I don't really like to use those names because we use the same names for derivatives in the first quarter of calculus. So we want to estimate natural log or approximate natural log of 15 by writing it in terms of the things I just mentioned so that we can approximate it. So notably, 15 is equal to 3 times 5. So we're going to write this as the natural log of 3 times 5. We're going to break it up as the natural log of 3 plus the natural log of 5. And then we're going to use the approximations. The natural log of 3 is approximately 1.1. The natural log of 5 is approximately 1.61. And then 1.61 plus 1.10 is 2.71. I'm still using the approximation symbol here because it's what the natural log of 15 is approximately equal to. So the natural log of 15 is approximately 2.71. I'll point out that if you use a calculator here, your answer will actually come out slightly wrong because it'll be more exact, but it won't use the approximations in the right way. So you really do have to do these without using a calculator to get the right approximation. I'm going to keep these in view so that we can still reference them. So let's go to the next one here. So I want to find now, sorry, let's get nicely in view here, the log of 12. So I'm going to just start breaking 12 up as the log of 3 times 4. And I can either write that as the log of 3 times log of 4, or I could have log of 3 plus log of 4. Let me back that up. Log of 3 times 4 is the log of 3 plus the log of 4. And then 4 is equal to 2 times 2. So I can write this as the log of 3 plus the log of 2 times 2, which is the log of 3 plus the log of 2 plus the log of 2. I could have also just jumped straight to the 12 is 3 times 2 times 2 and then broken it up as log of 3 plus log of 2 plus log of 2. I also could have instead said that 4 is equal to 2 squared, and that 2 can come down as a coefficient. So I could also think of this as log of 3 plus 2 times log of 2. Because this is also the same. It's 2 squared is kind of weird. 2 times 2 is 4. 2 plus 2 is 4. It's kind of funky. But you could also think of this as log of 2 squared. And then the 2 could come down in front. Either way, log of 3 is approximately 0.48. And log of 2 is approximately 0.30. So we're going to get approximately 0.48 plus 0.60. 48 plus 60 is 108. So 0.48 plus 0.60 is 1.08. Let's continue on. And I guess it might be hard to see. I'll move this off to the side. I'll reference it back and forth. So I'll just say the things and you can look at it on your own. So log of 5 is kind of funky actually because we don't have a log of 5, right? I kind of omitted it on purpose. So you have to think of how to write 5 in terms of 2 and 3 and 7. You might think 2 plus 3, but that's no good because we need things that multiply or divide the 5. Well, there's a trick here. And the trick is that this is log base 10. So you also know that log base 10 of 10 is equal to 1. So we can rewrite this as the log of 10 divided by 2. It's kind of a trick. And then that's going to equal the log of 10 minus the log of 2. And then we can say that that's approximately, well, the log of 10 is exactly 1. And the log of 2, according to our list over here, is approximately 0.30. So that's going to be minus 0.30. And that's going to be approximately 0.70. Cool. So if you see a 5 in there, that's what you're supposed to do. You're supposed to kind of think of 5 as 10 divided by 2, or think of some other tricky way to kind of get it. Natural log of 43, sorry, natural log of 49 divided by 3 is the natural log of 49 minus the natural log of 3 using the quotient rule. We can rewrite this as the natural log of 7 squared minus the natural log of 3. And then the natural log of 7 squared is 2 times the natural log of 7, still minus the natural log of 3. Now we're going to approximate. The natural log of 7 is approximately 1.95. The natural log of 3 is approximately 1.10. So when we have 2 times 1.95 minus the natural log of 3, which is approximately 1.10. 1.95 is almost 2. 2 times 2 is 4. I'm missing 0.05. 2 times 0.05 is 0.1. So this should end up being 2 times 1.95 should be 3.90 minus 1.10, and that's approximately 2.80. Cool. Couple more. These are pretty not terrible, but they do take a minute to get the hang of. They're really just trying to make sure that they're trying to force you to use the logs properties here. Let's look at this next one. We have the natural log of the cube root of 6/5. So first and foremost, I'm almost always going to rewrite a root as the corresponding fractional power. So the third root of a number is the same as that number to the 1/3 power. Cube root is a 1/3 power. Fourth root is a 1/4 power. So it's always a 1 over whatever that number is right there as a power. And then I'd probably use the power rule and bring that down in front. So that's 1/3 times the natural log of 6 divided by 5. Then I'm going to break that up as 1/3 times, and I do need some brackets here, the natural log of 6 minus the natural log of 5. So whatever I get in here, I'm going to eventually multiply it by 1/3 or divide by 3. I don't have a natural log of 6, but I do have a natural log of 2 and a natural log of 3. So this is going to be equal to 1/3 times 6 is 2 times 3. So I have the natural log of 2 times 3, or the natural log of 2, plus the natural log of 3, minus the natural log of 5. Now I'm going to use my approximations. I know that the natural log of 2 is approximately 0.69. So it's going to be approximately 1/3 times 0.69 plus the natural log of 3, which is about 1.10, plus the natural log, sorry, minus the natural log of 5, which is 1.61. Okay, let's see what we get. Make sure I got that right. Yeah, that's right. Sure. So we're gonna end up getting 1/3 times 1.1 plus 0.69 is going to give me 1.79. And if we subtract 1.61 from that, we're going to get 0.18. 18 divided by 3 is 6, so 0.18 divided by 3 is 0.06. Cool. This next one's a little tricky. I definitely don't have a 75 anywhere. And 75 is kind of annoyingly 5 times 5 times 3, plus it's the 0.75. So there's two ways you go about this. The less easy way is to just think of 0.75 as 75 over 100. But then you have to do 75 minus 100, and it's kind of like the fives are still a pain. The better way to do this is to reduce that fraction. So to first write it as a fraction as log of 75 over 100, or go straight to the fact that we know that 0.75 is like 75 cents, which is like 3/4, literally 3 over 4. This reduces to log of 3 over 4. And then we can write it as log of 3 minus log of 4. And I do like using the power rule. I'm going to write this as log of 3 minus log of 2 squared. And that 2 gets to come down in front. I'm going to have log of 3 minus 2 times log of 2. Log of 3 is approximately 0.48. I should use an approximation symbol. And log of 2 is approximately 0.30. So we get minus 2 times 0.30. So this is going to be approximately 0.48 minus 0.60, which is going to be a negative number. It's negative 0.12. It does make it's okay to take a logarithm and get a negative result, because what you're saying is you need 10 to a negative power to equal this number here. And that's always going to be true when you're taking a logarithm of a number between 0 and 1. Kind of like how I'll just do off to the side here real quick. If I asked you, like, what's log base 3 of 1/9, you're taking a log of a number that's smaller than 1, and that's equal to log base 3 of 1 minus log base 3 of 9, which is equal to log base 3 of 1 is 0. Log base 3 of 9 is 2. You get negative 2. And 3 to the negative 2 power is 1 over 3 squared, which is 1 over 9. So it does make sense that when you take the log of a number between 0 and 1, you do get a negative answer. So we should get a negative answer here, because 1 over 14 is certainly bigger than 0, but smaller than 1. So actually, I'm going to first break this up like I did over here. I'm going to get log of 1 minus log of 14. Log of 1 is 0. Log base anything of 1 is 0. So log base 6 of 1 is 0. Natural log of 1 is 0. Log base 72 of 1 is 0. So then we're going to write this as negative log of, what multiplies to 14? 2 times 7. Okay, here we have to be extra careful. I'm going to make a mistake, but I'm going to correct it. So the mistake here would be to write this as negative log of 2 plus log of 7. The problem here is that, well, actually, this is going to come out positive, and it shouldn't. Log of 7 is bigger than log of 2, and log of 7 plus negative log of 2 would be positive. The problem here is that it's the negative of all of this, and all of log of 2 times 7 is equal to all of log of 2 plus log of 7. So we need brackets around that, or some sort of parentheses, so that we can distribute the minus sign. I might wait to distribute the minus sign until just doing the addition first. I'm going to say this is approximately negative log of 2 is approximately 0.30. Log of 7 is approximately 0.85. So I end up getting approximately negative 30 plus 85 is 115, so 1.15. So negative 1.15. That looks kind of trashy. Sorry about that. It looks kind of ugly. All right. Is that the last of my logarithm examples here? Nope. Oh, yep, maybe. I think that's, see what's on the next page. Nope, couple more. Oh yeah, a couple more. So natural log of 6e cubed, it's totally fine to write this as the natural log of 6 plus the natural log of e cubed. The natural log of 6, I'm going to break that up as 2 times 3. So it's the natural log of 2 times 3. And the natural log of e cubed is 3 times the natural log of e. Natural log of 2 times 3 is the natural log of 2 plus the natural log of 3. And it's really important to know that the natural log of e is just equal to 1. Right? Just off the side here, the natural log of e is really just an abbreviation for log base e of e. And so this says e to what power equals e? Oh, it's got to be 1. There's no other choice. So here we're going to get approximately the natural log of 2, which is what, 0.69? Yes. And then the natural log of 3, which is approximately 1.10, plus 3. So I'm going to get 0.69 plus 1.10 is 1.79 plus 3, which is going to be 4.79. Not too bad. Same kind of deal is going to happen here. I'm going to rewrite this as the log of 9 times 100, recognizing that 100 is a power of 10, and so I shouldn't try to break it down any further. So I'm going to break this apart as log of 9 plus log of 100. And just like here, log base e of e was 1. Oh, sorry, you can't see that. Just like up here, log base e of e was 1. Log of 100 is really log base 10 of 100, right? It's just an abbreviation again. And you're saying 10 to what power equals 100? Oh, the power is 2. Or if you prefer, you can even say log base 10 of 10 squared, and then that 2 comes down. And you get 2 times log base 10 of 10, which is just 2 times 1. So that's going to be a 2. And then for log of 9, we're going to rewrite that as log of 3 squared. We're going to use the power rule to bring the 2 down in front. So we're going to have 2 times log of 3 plus 2. And then we're finally going to approximate and say that log of 3 is approximately 0.48. So then I'm going to get 2 times 48 is 96. That's going to be 0.96 plus 2, which is going to be 2.96. So that is how we use known values of logarithms or known approximations of logarithms to approximate more complicated things without a calculator. All right, let's look at the last couple things here. There's just a couple more things. We're almost done. Some simple interest. So the way we calculate simple interest is by taking the principal, which is the amount of money you start with or the amount of money you invest, and multiplying it by 1 plus the interest rate as a decimal. So if they said the interest rate was 7%, the decimal will be 0.07. They said that the interest rate was 23%, then the decimal will be 0.23. You don't need that 0 before the decimal point, but it's fine to write it. Finally, the time is going to be the number of years. And then you can write it like, and then A is the amount of money you have after that time. So sometimes we just write capital A, sometimes we like to write A of T to really emphasize the fact that the amount of money depends on the variable T. But sometimes we don't. Most of the time we don't, actually. So let's look at these examples here. So suppose $600 is invested into an account that earns 4.5% annual interest. How much is in the account after 10 years? Well, I'm just going to throw numbers into a formula and then I'm going to use a calculator. Do I have my calculator? It's right over here. So it's still good to write out the formula. So you need the amount of money after 10 years, if you want to write it this way, is equal to the principal, $600, times 1 plus the interest rate, 4.5% is going to be 0.045. Right, you're moving that decimal over 2 places, raised to the 10th power. Not too bad. I would simplify this just a tiny bit before using a calculator. So it's 600 times 1 plus 0.045 is just 1.045 to the 10th. If you didn't have a calculator and you were asked to do this on an exam, this would be your final answer, which again is not very informative because you're like, I don't know how much that is. I don't know how much money I have after 10 years without using a calculator. So let's use a calculator. Oops. And here's the way I would do it. I would start by writing 1.045 raised to the power of 10. And then I would multiply that by 600. And then if I wanted 2 decimal places, because usually we do 2 decimal places, we're talking about money, so you can get the right amount of cents. I would round this to approximately $931.78. Cool. All right, so the next one. How many years until the account reaches $1,500? For most of these questions, you'll know 2 of the pieces of information and have to find the missing one. So in this problem, we know, I guess we have 3 pieces maybe. We know the principal, we know the interest rate, we know how much time for this one, we're trying to find the amount of money. In this problem, we know the principal, we know the interest rate, we know how much money we're going to have, and we're asking how much time does it take. So we're still going to write the same question, just fill in the blanks, fill in the things we know, and we'll solve the thing we don't. So the amount of money we want to have is $1,500. That should equal $600 times 1 plus the interest rate as a decimal raised to the we don't know. So I'm going to write T for time. So I'm going to solve this. So I'm going to write, I'm going to first divide both sides by 600. So 1,500 divided by 600 is equal to, I'm going to write this as 1.045 to the 10th power. I should simplify 1500 over 600 as 15 over 6, or really 5 over 2. So I'm going to rewrite this as 5 over 2 equal to 1.045 raised to the teeth power. And as we've seen in some of the previous problem sets or homework assignments, if you have some exponential equation where your exponent is a variable, the way we usually solve that is by using a logarithm. I would default to the natural log. So I'm going to write this as the natural log of 5 over 2. You could also write 2.5 here, but I'm partial to fractions, is equal to the natural log of 1.045 to the t power. The reason we do this is so that we can use the power rule for logarithms, and this power that's t can come down in front. In fact, I like to write this little arrow here. I know it doesn't feel like a big deal, but it makes it easier to be like, oh yeah, that gets to come right down there. So then we're going to say that the natural log of 5 over 2 is equal to t times the natural log of 1.045. And then finally, we're going to divide both sides by the natural log of 1.045 to get the t is equal to the natural log of 5 halves divided by the natural log of 1.045. That is the exact answer. But again, not very helpful. I don't know what that number is really. Is that 2 years? Is that 7 years? What do I know? So I should use a calculator to approximate this. I will point out that when I use a calculator, I will probably write 2.5 instead of 5 over 2 because it's just easier to type. So I'm going to do the natural log of 2.5 divided by the natural log of 1.045. I'll point out that if I did it, oh, sorry, you can't see that very well. I'm so sorry about that. The natural log of 2.5 divided by the natural log of 1.045. It's about 20.81. I'd point out that if you wrote it the other way, the natural log of 5 over 2 divided by the natural log of 1.045, you'll still get the same answer. 20.82 is what I rounded to, 20.82. So t is approximately 20.82 years. So 20 years and what, 8/10 of a year, 4/5 of a year. I don't know. It's like, what's 80% of 12? Like 9-ish months, I guess. And then last page, a couple more of these. So new setup. Suppose James invests $800. Oh, I'm James, by the way, in an account, and the value, did I? Okay, I was like, am I recording this? Yes, I am recording that. I was worried for a second I'd done all this and not recorded it. Suppose I invest $800 in an account and the value doubles in 6 years. What was the approximate interest rate? So now, same equation. A equals P times 1 plus R to the T. The amount I invest is $800, so that's my principal. I don't know what the interest rate is, so that's going to be my variable. I know the time it takes is 6 years, and the amount I'll have after 6 years is double what I started with. So double 800, 1600. So again, we should always be able to fill in essentially every piece of information except for one thing that we're going to solve for. So here I would first divide both sides by 800. So 1600 divided by 800 should be 2 because it's a doubling time. That's going to be 2. 800 divided by 800 is 1. And when you have multiplication, you don't divide each piece by 800. You're just dividing the whole thing by 800, and that means that's going to be 1. So I have 1 plus r to the 6th power. To undo it, so I'm not going to use a logarithm here. You could technically use a logarithm, but it's the wrong way to go. The better way to go is to undo a 6th power by raising both sides as 6 roots. So I'm going to write this as 2 to the 1/6 power equals 1 plus r to the 6th to the 1/6 power. You really don't need to write this right-hand side. I'm just trying to show my work here. This is 2 to the 1/6 equals 1 plus r, all to the first if you really wanted, but I don't think, right, so it's right to the first. So 2 to the 1/6 is equal to 1 plus r. And then if we subtract 1 from both sides, 2 to the 1/6 minus 1 is equal to r. Or r is equal to the 6th root of 2 minus 1. Again, this doesn't super help me if I don't have a calculator. So I'm going to take the 6th root of 2. So using a calculator, I would write it as 2 to the 1/6 power. There is a button here. Yeah, there is a button for the 6th root of 2 right down there. I don't love doing that, but I guess I could do it that way. Can I do it that way? Nope. So let's see. So you have to do like 6th and then the root. Yeah, that's terrible. I do not love that at all, but it's fine. It gives you about 1.122, or you could do it what I think is the better way, 2 to the power of 1 divided by 6. Same result. Either way is fine. Do what makes sense to you. But I would encourage you to get comfortable, very comfortable with knowing that 2 to the 1/6 is the same as the sixth root of 2. That has to be something we get good at knowing how to do. So then we're going to get that R is approximately 1.12. Let's go a couple more decimals here just to be careful. I'll round that 4, 6 up to a 5 minus 1. So then that's approximately 0.1225 or approximately 12 point. Now here I've actually made kind of an error because I really wanted to round to the nearest tenth. And if I was going to look at just that, rounding it to the nearest tenth, I would round it up to 12.3%. But I should, if I actually go back and look here, I have, 12.246. If I go a little bit further, rounding it up to the nearest tenth, it's actually, or rounding it to the nearest tenth, 12.246 rounds up to 12, sorry, rounds down to 12.2%. If it was 12.25, it would round up, but it shouldn't actually be 12.25 because I don't want to round twice to help me get higher. All right, how long will it take for the account to triple? So now we're going to use this percentage, and I am just going to use the approximation of it. So I'm going to say I want my everything else here to be the same. So I'm going to have the 800 times 1 plus my percentage as a decimal, so 0.122 raised to the how much time it's going to take. I want that to triple the initial amount, so that's going to be 2,400. Or really, we could be smarter about this and just say, we could have said 3 times 800. Because then if we divide both sides by 800, 3 times 800 divided by 800 is just going to be 3. So dividing both sides by 800, we get 1.122 to the tth power equal to 3. We're going to use a logarithm here because, again, our exponent is the variable, not the kind of base thing right here. So the natural log of 1.122 to the t equals the natural log of 3. T times the natural log of 1.122 is equal to the natural log of 3. So we're going to get the t is equal to the natural log of 1.122 divide. Nope, no. Sorry about that. T is equal to the natural log of 3 divided by the natural log of 1.122. Again, it doesn't tell us very much. I'll point out it took 6 years for my money to double. If we went 12 years, the money would double again. So double, 6 years it doubles, 12 years it quadruples. We're not going to just split the difference. It's not going to be 9 years to triple. It's going to be something actually different than that. You can't just kind of divide it up into equal lengths of time. So if we find this here, the natural log of 3 divided by the natural log of 1.122. And again, that was already an approximation, so we should definitely use little squiggly lines here. It's going to be approximately 9.54. So close to 9, but not exactly 9. And it is important that it's not exactly 9. So the number of years is about 9.5 years to triple. All right, that is all I have got. Yep, that's all I've got. So I hope you watched the video and I hope you liked it. I'll see you all on Friday.